All right, can you hear me now? No. All right, you can hear me. Oh, I still have folks reporting they can't hear me. Great. Let's see if I can fix this. Ariel. Okay, we do have some folks who can hear us. April, can you hear me? I see. All right, cool. Well, let's get started then. Um, First, I want to thank everybody for coming today. Good morning, good afternoon. I'd love to know where folks are viewing us from. I'm here in Colorado, here in the U.S. My name is Jim Moffitt. I'm a developer advocate here at Tinybird, and I may be joined by our field CTO, Ariel Perez. And as I was saying before, which I don't think anybody could hear, was that I was looking forward to Ariel being here because was a former power user of Tinybird before he joined us as our field CTO. So I know he has lots of real world experience working with Materialized Views. And let's get started. So the topics today, I'm going to provide an introduction to Materialized Views, the why you would use them, how they work. We'll talk about some of the most common use cases that our customers use Materialized Views for. And then for the rest of the session, we'll actually start working with Materialized Views. I'll be building a variety of different types of Materialized Views. I'll talk in a little bit about the data that we're working with today. But part of the exercise is splitting this data, which has different types of actions associated with it, and splitting those actions and setting them into different action-specific tables. I'm also going to show how Materialized Views can be used to help deduplicate data. I think duplicate data is a reality that a lot of our customers, and certainly I have dealt with in the past. Often you have emitters who are sending, maybe it's an IoT network or some other source. And in the end, they often provide duplicate data, which presents different challenges for managing it. And then we're going to be doing some pre-computed aggregates. And that's one of the superpowers of Materialized Views as implemented in Tinybird, is how you can essentially pre-compute aggregates as data arrives. So you only perform the work to maintain the aggregates when data first is ingested, and then it's available for as many queries that ask for that data. So I first want to start with just a few minute context for about what Tinybird is, assuming that we have folks here who may not be that familiar with what Tinybird is. First, at its core, it has an OLAP database as its data layer. We have built Tinybird on top of ClickHouse, the open source ClickHouse. And I'll say that Tinybird and our engineers are some of the most frequent contributors to that project. Tinybird, I see it certainly as a platform for unifying data sources. We have a whole suite of native connectors for things like Kafka Streams, Confluent, Redpanda, Snowflake, S3, BigQuery. I mean, it's a growing list. But if you have data that lives in many different places, Tinybird's a wonderful place to easily get that data into one platform so you can join that data and start doing your analysis. Which brings us up to the third thing of what Tinybird is. We are a data analysis platform. You bring this data into Tinybird to join, filter, aggregate your data, perform different types of analysis. Maybe you're doing temporal roll-ups. Maybe you're joining data from different sources to come up with good looking, you can think of them as reports, and also real-time processing. That's our real strength. So, and Tinybird is also a place to design and deploy API-based data products. That was really the first thing that caught my eye about Tinybird, was the ability to bring data in, use skills like SQL that I've had forever, mash up the data, get to a data view I am happy with, push a button, and host that as a high-performant real-time API. That pretty much blew my mind, and one reason I'm here today. So this next view is sort of a architectural diagram that hopefully will illustrate where we sit in a real-time data pipeline. So in this case, we're sort of looking essentially at like a Kafka stream where you have a data source. It's publishing and generating data. It arrives at this event bus, which knows, of course, the data coming in, but also knows subscribers that are listening to different topics in the case of a Kafka stream. So inside Tinybird, we have a native connector for Kafka, this event listener. And then that feeds into a real-time database. That database engine provides an SQL engine where you can just go to town with your SQL skills and analyze and massage that data. You get a data view that you are happy with, and then you literally push a button and you can publish it. You can host it as an API. We also have a growing options for sending data to data sinks. Our first example there is like if you want to send data to an Amazon S3 instance. So let's get into, this will just be a few minutes of kind of presenting all things about materialized views, and then we'll start working with Tinybird and building some. So what is a materialized view? One of the key concepts is that it is taking data as it arrives and performing your transformations on those small data blocks that keep arriving. So in a sense, it's doing pre-computed, it's doing all the work upon ingest, making them all available for any time a query comes in. So this really helps provide up to the second results. Materialized views are implemented in many different ways across different database systems. And what makes it special with Tinybird and is that it's essentially a real-time process. It's incremental, and things are triggered as data arrives. There's other systems like Postgres where they have materialized views, but it's a very manual process where you schedule it. You might have to do it every couple hours. You might want to do it at least once a day to get these new views set up. But the drawback with a lot of these systems is that it is basically doing a full rescan of all the data to come up in materialized views. Whereas with Tinybird, it's incremental and happens as data arrives. These materialized views, they support complex queries and aggregations. If you're familiar with Tinybird and have developed very involved pipes with lots of nodes with great SQL, just know that applies equally well to materialized views. They support a variety of fundamental use cases. We'll talk about that more in a minute. And also it supports real-time use cases and patterns. And again, that's what really makes materialized views within the context of Tinybird so special.
Jim, can I add something else on that? And I've been in the background.
Yeah.
One of the things that absolutely, I think for folks to get through right here and really if it sinks in your head is when you hear materialized view in Tinybird, which is powered by ClickHouse Materialized Views, these are not your traditional OLTP SQL database materialized views. These work in a very different way, where the key thing to remember is that in most database systems you're used to is that materialized views will be a snapshot of the data as of the time when you refreshed it, because those things, as Jim was saying, have a schedule. So it'll allow you to copy a bunch of data, do a bunch of joins and logic, write that to now a table, and that's now materialized, and that data is in that table. You can query from that table without doing the joins, but it's as of the time you updated it. With Materialized Views in Tinybird, the key thing is this happens as the data is being ingested. So this Materialized View is being kept up to date in real time as the data is streaming into the platform. So that's a huge difference there, and it allows for so many amazing capabilities. So that's the thing I want to make sure like people walk away with, that these are not your traditional grandma's Materialized Views, right? This is a very different flavor now. These update in real time on insert. These are based on insert triggers.
Yeah, those are good points. And I have to believe that for all those reasons, that's one reason ClickHouse was picked as a data layer to build Tinybird on top of the fact that you really do have that real-time nature behind it. So I'm going to show a series of different visuals just to kind of help us all get some context about how these things work. And this diagram, as you see, goes left to right, where you have new data pieces coming in all the time in real time. You have this landing data source where there's already a set of existing data that's been there for, a long time probably, while you have these new data pieces arriving. And then the materialization process involves a transformation pipe. And that is a thing that takes the data from this landing data source, does something to it. It might do some filtering, might do some aggregations, what have you, and then it produces this materialized view, which is actually another data source. So you're taking a landing data source, you're transforming it in real time, and you have this materialized view that then you want to work with. And here's a little graphic showing. On the left, what you have is like this archive, this already processed chunk of data. You can imagine these characters A and B, maybe they're like page views or product purchases, whatever they are. You have this corpus of already processed values, and then you have these new chunks that have arrived. And then you have this merge process, which even if you don't do anything behind the scenes, these mergers are triggered every few minutes. And then you get this final view of all the data aggregated together. And the key thing about Tinybird, which we'll be talking about, is when you're building with materialized views, you have different mechanisms for triggering that merging process on the fly when that query comes in. It's hard to talk about materialized views without at least providing a short introduction into these database table engines. So every data source in Tinybird is built upon one of these engines. And Tinybird implements the MergeTree family of ClickHouse table engines. And MergeTrees are they're amazing for many reasons. They're based on columnar storage. Everything's stored in columns. So this design drastically reduces the I/O for analytical queries. This family of merge trees can handle just huge volumes of data, both in terms of storage size and the number of rows. Is designed to work both efficiently as a single node, a single instance, but also can be, scaled horizontally across a cluster, say. These engines are optimized for fast data ingestion and querying, and it makes it suitable for scenarios with high put-through insertions and also complex analytical queries, which is exactly why you come to Tinybird to build things. A couple of notes. There's the standard merge tree, but there's some other flavors that are commonly used within the world of Tinybird. One is the ReplacingMergeTree, and it's best when you need to manage the latest version of data or you want to remove duplicates. And it's something that we'll be demoing in a little bit. There's also a summing merge tree, which, as the name implies, is built to help you count things and sum up values, and we'll show an example of that. AggregatingMergeTree is sort of it includes everything that the summing merge tree provides, but also lets you do averages and mins and maxes, those types of attributes that you can build these aggregations on fast moving real-time data and know you're getting up to the second good results. And then there's another one. This is called the collapsing merge tree, and there's also a versioned collapsing merge tree. And this will not be part of my demo today, but I at least wanted to spend a few seconds on what this is all about. And what the collapsing merge tree is great for is for when you have events coming in. And in this case, we show a simple little log of users logging in and out of the system. And you'll notice that column sign. So when the sign is sent in as a 1, that reflects the current state. If you send one in with a -1, that kind of negates that and it marks that data point as something that you can forget or delete. And down below, I have a simple query where I'm summing the signs across users. I'm grouping by user IDs. And I'm looking for anyone who has that sum that's greater than 0, meaning that they're still logged in, they haven't been logged out. And so if you run that query, you'll see from this brief, concise data set that it comes back and says only user 3 is active. So this is just a visual of what you can do. It's collapsing because you're using the sign field to negate, to remove, to forget certain data points. I have not used this yet, but I think certainly if we have another session on materialized views, this would be an interesting one to build a demo for. So let's get back to what is a materialized view. You can see that schematic on the right. It's really consists of two things, the things in the blue box. First, you have a transformation pipe, and this thing is pulling from a data source, and it's applying SQL to it. And we'll talk in a little bit. We'll show how, when you're doing aggregations, at least, you can use a state operator, which tells the system that you want to maintain intermediate state, temporary state, that then when the merge process is triggered, it all gets merged together. The second part of a materialized view is this data source that you're using the transformation pipe to create. And a data source that provides merge data that is a combination of already transformed data plus the new parts. So let's go through these in a little bit more detail. First, you have a data source that you want to work with. And I'll be referring to this probably as a landing data source. This is where data from the outside world first lands in your instance of Tinybird. Typically, these are set up as merge trees, but there may be cases where you want to do some deduplication right off the bat. You might have stuff landing in a replacing merge tree. But typically, this data source, at least with the customers we work with, they're receiving massive amounts of real-time data with duplicate data. So then we have a transformation pipe. This is a set of SQL-based queries that transform that source data, and it writes it to a target data source. And of course, this SQL is used to filter, aggregate, join data. And the sorting keys are used to help identify basically what your primary key is, to help identify duplicate data. So when you set up your transformation pipe and you're working in the context of materialized views, one of the first things you have to do is decide what table engine to create and write to. And also, if you're using the summing and aggregation merge trees, you will use state functions, the state function form of any of your aggregates. You can see down here below let me go back. Here you have a count state, for example. That's telling the system that, hey, as data is coming in, I want you to maintain these intermediate states of all the different data blocks that have shown up. And then when the merge process is triggered, you're going to merge all those pieces together.
Jim, can I add a little more there on state? Because I think state is something that, unless you specifically work with Tinybird and ClickHouse, it won't click immediately. And often the thing that state helps you solve for are things that can take a lot of work in other systems. So the idea of state is to allow you to maintain partial calculations of something, partial statistics, so that at read time, the aggregation result is actually much simpler to calculate because you've maintained the aggregates. The one that's easiest to understand, like the impact of this, is when you have an average. So assuming I have 3 rows and each one is an average of thousands of results, another one is an average of hundreds of results, another one is average of tens of results, the average across those 3 rows is not the average of the averages. That is, a fallacy, misunderstanding of mathematics and statistics. But what you do know, it's going to be the weighted average of each of those. At its core, when Tinybird is storing the state for an average inside of MV, what is storing, it's the weighted average for each one. So that no matter what, however you aggregate it, you might aggregate by any of the other columns. When you roll up the average, you now have a correct average, and it's based on the average of the, not the average of the averages, but of the weighted averages of each of those rows. So that's kind of what's happening. And it does this for a large amount of statistical calculations. And that's how it, gives you a lot of power here, where in one row you can store the data of thousands, hundreds of thousands, tens of thousands of rows in a statistically valid way. I don't need to read the original 1,000 rows. I just need to read this one aggregated row that's holding the state for me. That's a key thing. It makes it very powerful.
Yeah. Thank you for that. And keep these comments coming. And then, after you have your transformation pipe, you are writing those results to this new data source. And when I build these pipes, I often give them a name like feed, like I'm feeding something. I'm taking real-time data and I'm feeding it to the second data source, which in the big picture, we can kind of refer to this new data source as the materialized view. That's the thing we're after. That's the thing we're building. We've now built it. Now we can go off and use it. So common engines for this, again, are the ReplacingMergeTree. That's a common table engine for deduplicating data. And we've talked a bit already about the aggregating and summing merge trees. And that's when you need to do real-time counts, totals, mins, maxes, and averages. And then once you have that materialized view set up, you have this new data source being populated with the data transformed the way you want it. And then, of course, from there, you build a publishing pipe. And again, this is a set of SQL queries that transform that data that's been written to the data source. And these SQL queries also determine how the merge process is managed. These pipes typically publish to an API endpoint. Maybe you joined our session last week. I did one on MongoDB. That was an example where I actually had some materialized views, and then I published an endpoint, which for the context of last week, that was all about, hey, you can use Tinybird to publish real-time data that's flowing into your Mongo database. So the SQL that you apply in these publishing pipes, they apply the merge functions, which work with those state functions that you set up in feeding the materialized view. Well, you use here, you can see over here on the right, the count merge. And what that's doing, that's telling the system, okay, I've asked you to maintain this state for these aggregates. I now have a query. I want you to go right now and merge that and send me those up to the second results. Also, there's the final keyword. That is very important for things like replacing merge tree tables, where it's really the same thing. Like, okay, I'm doing a query. I want the final up to the second view of the data. In the case of replacing merge trees, I want you to have already knocked out any duplicates and give me that final result. So let's talk about why use materialized views. We've touched upon some of this already, but the big ones in my mind are schema evolution. You can imagine you're pulling in, maybe you got the credentials to some Kafka stream, and in that topic, you can imagine a very wide set of attributes. Maybe you're bringing in 20 attributes per event, but in your world, you only need maybe 5 or 6 of those. So these materialized views are an excellent way to drop columns, like take from the big source and transform it by dropping columns into a more concise, less data to process type of table. Same thing with sorting keys. As you design these Schema is you tell the system, how do you want to organize and then retrieve that data? And often you have, a lot of that is driven by the use case. You may have a scenario where maybe it's product data, and you also have a customer layer there. In some cases, you may want to sort by product IDs mainly, so you'd set that as your main sorting key. But for other consumers of your system, maybe the customer ID is the way you really want to first organize that data. So long story short, you can set up different tables with different sorting keys. Now, I've talked about deduplication. Again, materialized views can play a role in that, but also know that, in fact, we have a guide. In fact, I have a set of resources, and that reminds me I should share. You'll get this in an email, but I have this repository I set up for this workshop, and it has a lot of the material from today. But one of the things I have set up is just we have a lot of different guides and core documentation, blog posts about materialized views, and this is a good place to go after this session and learn more about this stuff. And also another common use case for materialized views are these pre-computed aggregations. And again, being able to do that work as data arrives, making it ready for whenever those thousands, hopefully, queries come in for the data.
And can I add something there? Right? Can you go back to that for a moment? Especially for all of these, right? Whether it's schema, especially schema evolution and deduplication, we might think about the fact that, I have an underlying data source and the sorting key is a certain way. I have a use case where I want to query it a different way, but I don't want to change the underlying schema, or maybe I want to make a change to the schema, but I don't want to change the underlying table. NMV is a straightforward way of saying, hey, let me kind of pivot that table and create it in a new way. Your first question might be, hold on, wait a minute, I'm duplicating a lot of the data for that. Why can't I just slap an index on it like another database? There's a few reasons why you can't just quote unquote slap an index on it. There are some kinds of indices in ClickHouse, but they don't work the same way as they would in your traditional RDBMS. So since you can't really just slap an index on it, and that's a whole other topic of thinking about columnar databases and data skipping indexes and things like that, you can create a copy. But then your argument is, wait, hold on, why am I going to copy it? That's, what if it's a massive table and copying a bunch of data? At its core, when we think about what's happening here, how we're optimizing queries for absolute massive speed and performance, at the end of the day, data is cheap, storage is cheap. And as we, we've recently gotten to a place where, a lot of our underlying storage is actually cloud storage. Like storage is actually pretty cheap, and we don't need SSDs and super fast disks to actually make the data make it perform fast. So if it's actually better for you to pivot in another way and store more data, another copy, and our system and the MVs keep it up to date and in sync, then that's the way actually you get the performance out of it. So, I just want to make sure that might come into people's heads, like this requires me duplicating, but there's actually value in that duplication, and storage is cheap versus CPU. If you want to use more CPU versus more storage, definitely go more storage because it's going to be cheaper for you if it achieves the performance you're looking for.
All right, thanks for that. I want to give another view of how these materialized views work, and this may give you a sense of the complexity that's involved here. This is actually from ClickHouse recently put out an article. It's basically it's about their architecture, how they design the system. But there's a good chunk of information in here about materialized views. And so I, just as a second view of how these things work, I wanted to show this. Here, this is sort of the top of the funnel, where at the very top you have new data hitting your system. And then in that transformation query, you see a pretty standard looking SQL where, again, we're using these state functions, telling it that, hey, as data comes in, I want you to maintain the maximum value for this data and also an average. And in this case, this system is looking at latencies. So it does all that, and then it maintains these parts, these blocks of data. And then on the other end, when the merge happens, and in this case, its merge is being triggered by an explicit query using the merge keywords there, the merge operators, it's taking those parts and doing all the work that Ariel was just talking about and merging it with the data that's already been processed. So this is, I think, a very effective diagram for illustrating the different moving pieces here and how the two queries, the transformation, and then the query for getting the final result works. A couple things before we jump into the demo part of today is some things to keep in mind. One is that some SQL functions just will not work as expected. And the reason for this is that, remember that transformation pipe is being applied to just a small block of data. So things like order by, distinct, and limit, it's all within the context of that small block of data. So while, in theory, you could use these type of functions, just know you're not going to get the results that you may expect. And another thing to keep in mind is the challenge of chaining materialized views together. And basically, replacing merge trees cannot guarantee unique data in downstream data sources that are not of the same replacing merge tree. And one way to think about this is that these are all insert triggers. So as soon as new data arrives, yes, it would trigger replace and merge tree, but that data essentially is instantly sent downstream to that aggregating merge tree. And at that point, you might have duplicate data again. Ariel, I don't know if you have experience with the challenges of chaining.
Yeah, and also like one of the things that I wanted to talk about is like why exactly it's a challenge, right? And I think you were getting there, and you covered it, and it's reiterating the idea that when the way a replacing merge tree does its thing. Cassia, hold on. The way a replacing merge tree does its thing is that as blocks are coming in, the data's coming in, and it has its merge algorithm and its replace algorithm. That happens on a schedule. But as we said before, the power of MVs in Tinybird is that as the data comes in, it gets triggered downstream. It's an insert trigger. So what happens is that if you chain different materialized merge trees downstream from a replacing merge tree, is the data will be propagated before the RMT gets a dedupe. And that's the problem. So you cannot get the guarantee of dedupe downstream because, again, since merges happen on their own cadence, on their own schedule, the ClickHouse internals manages that, you cannot guarantee that you'll get a truly deduped view in the downstream. It'll be triggered and propagated before it truly gets deduped by the engine.
Yeah. So it's certainly something to keep in mind, and just know we have a fleet of sales engineers who are working with our customers continually about issues like this, about how to properly design and work with materialized views in these respects. And just know that there's several options for deduplicating data, and a Lambda design is a mix of these batch and these speed layers. We do have a couple great guides around this. I'm going to switch back to this. This one here. If you're interested in a more complex architecture, again, one that is this is the one where it talks about how the pitfalls of chaining these things together, but then offers a solution that actually uses copy pipes to keep your data, in this case, deduplicated. Highly recommend this guide for those reasons. Again, these resources are in that repository. If you go to our GitHub and just just type in Materialized Views Workshop, you'll get this. So let's start working with Tinybird. And what I have here is, excuse me, I built a data generator that simulates, here, I'll show you some visuals around this. So what I have is for my source data, I have a script that's emitting actions. These are product specific actions, and there's different types. You can view a product, you can put it in a cart, you can take it out of the cart, you can purchase it, and of course you can return it. And the script, while it's running, does enforce some basic logical rules. I'm kind of a stickler for working with real data. Like, I don't want people to uncart a product that never was in the cart. So anyway, it has this thing enforces a set of rules about things like that. What's the true evolution, the life cycle of these actions? Another example is you can't return a product unless it was first been purchased. Quick view of the type of data this data generator is sending. One thing to notice here, this is a view event. Notice that there's here, let me zoom in a little bit, make it easier to see. You have an event where this is a view event. It tells you that when it happened, what customer viewed it, what was the product they looked at. The thing to notice here is for purchase events, when those happen, there's another attribute that's included in the source, and that is obviously the price of the thing that was purchased. So let's go back here. So what I have here, I have a mix of data coming into this landing data source. And the first thing I want to do is I want to separate these actions into their own tables. I want to do lots of analysis on the views that these products are getting. I want to do hourly views. I want to know, the top 10 viewed products, what have you. But I also want to have a purchase table that has all the revenue information I want to extract. So let's build something here. So I'm gonna build a pipe, and I'm gonna call this, let's feed the views table. And this is sort of my own convention. Of course, you can call these things anything you want. Here, I have to give it a unique name. Here, let me check one thing. I have a lot of different. Here, I'm going to eliminate this because I'm going to go back and recreate it on the fly. Because the importance of doing that is there's a UI, of course, that I can use to do this. Okay, so and I'm exercising a new feature that I've been using quite a bit. Lets me show different views of this workstation. So let's start over. Let's do feed views MV. And my first node, it's going to be quite a simple one because all this thing is going to do is send any new data into a new data source. So I'm going to do I want to pick timestamp. I want customer ID, and I want the product ID and I want to pull this in from my eStore stream. And I'm simply going to select where the action is equal to view. And let's run this and make sure we're getting what we want. Okay. So now I have this thing I want to that I want to publish into a new data source. So I come up here, I'm going to create. I only have one node, but you may have several. And I'm going to create a new data source from this query. And I'm just going to call it views, materialized view. That's my convention. I do that just so when I look at my data sources, I can be quickly reminded which ones are coming from a transformation query, which ones aren't. Here's some sorting keys. I'm probably going to retrieve data by product ID more so than customer ID. I'm often going to be looking at timestamps probably in most queries. That's all good. And here you can change the engine. I've talked about, I can set this one up as a replacing merge tree, for example. You could leave it as a merge tree if you want. And I have to give it a unique name. And here you have an option to, depending on how much data you're working with, you can, defaults to just processing and bringing in the last 2 million rows. Or you can select, this is what I usually do. This just brings in everything. You may have a case where you only want to materialize new data from the point of this creation. But this step is very important, and it shows how Tinybird will help you what we call populate a materialized view. You may have been collecting data for months or for even longer. And often when you build these materialized views, you want to process all of the data, and that's called the populate step. So what this is going to be doing a lot of work. I have 6 million rows, and if I hit this, I now have here, I'm going to take off my tag, and I now have this new table. Let me show it to you. So what we have here, these are only views coming from my source table. Now I've gone ahead and I've done that for all of these different action types. So if I click to this view, you can see that I have different transformation pieces. This one, for example, it's not going to be much different. It's pulling in the cart actions. Here's an example of where I'm building a table that's just of purchases. And what this brings to the table is one little twist. And as I showed in this view of the JSON that I'm working with, I'm pulling in for purchases, there's this extra price attribute that's in this product object. This is a nested JSON object. So if I go back, you can see here I'm extracting float from this product info column, and I'm going into that nested JSON and I'm picking out the price. And this is yet another example of where you can use these materialized views to kind of clean up and massage your data. I don't want to have to extract into my nested JSON every time. I want to set it up just once. And then what I get out of that, if I go to, let me take off that. If I go into purchases MV, you can see what I have here is a much cleaner view of the world. I just have timestamp, customer ID, product ID, and I've extracted that price out of the nested JSON. So another thing to show is for returns. My user story here is that these returns, they need their own table because I have some other group who manages how these returns get handled. They need their own data source to work with. And what we're showing here is that I'm doing a join. I have the products table in my project. This is just there's 500 different products, gives you a brand, the model, the price, the number on hand, etc. And what this query is doing is it's joining. It's just pulling in from the product table. This other group wants all the meaningful data they need in one data source. So I'm bringing in the brand and the model and the price from that product table. And just know, because of the way this join is written, whatever is on the left side is what is the data, is the stream, and that triggers every time there's new data coming in that stream, and it's a return action, this thing gets triggered. So what I have as a result of that, as you can see, this table is a little bit different. I've changed the schema. I now have this brand and model running. So that's the first example of using materialized views to separate out these different objects, these different actions. You may have a lot of different reasons why you want to delineate those into their own tables. And let's now talk about duplicates. I have a couple resources dedicated to that. So what I have here is a duplicate state. I have a separate data generator running, and it's set up to send in lots of duplicates. You can set a percentage, and I think I have around 20-25% duplicates. I've been running this since yesterday. I have 72,000 rows in here. So let's do some work to deduplicate these things. So to do that, let's build another pipe. And I'm going to add a tag just to add it to this topic. So I'm going to call this, let's call it, I'm going to be setting up a replacing merge tree. Again, that's an engine that's really good at helping deduplicate data. Let's build our first node. And we're just going to have one for this one as well. I'm going to call, we can call that whatever. I'm going to say, let's just give it a different name. I'm basically going to be selecting all from duplicates. So let's come down to the query. And I'm going to actually do a select all from duplicates. So every time a new chunk of data comes in, it'll basically send that to as an intermediate block of data. And I'm going to create Materialized View here. I'm selecting that node as the one I want to publish. I'm going to create a new data source. Let's call it deduped RMT. Back to sorting keys. I've just been in the habit of changing the order here a little bit. Let's go to the advanced. And this is where you can say, nope, I don't want a merge tree. I want a replacing merge tree. And that all looks good. And let's bring in, I have 3 million rows. So let me go back. Let's show. There it is. I'm going to add this to the duplicate subject. Go back and filter on that. Okay, so here we have the different players for this scenario. We have this new table that we've set up, and I want to do a couple things here. Here, I'm showing how much data we have in the deduped table, and how many are in the table that has tons of duplicates in it. So I'm looking at the last 10 minutes of data. And we have 126 duplicates there. This query I'm using, it's one that uses a subquery, but it goes in and looks for double counts of things that are grouped by the timestamp and the product ID. Now, if I run the same thing against the deduped version, you can see I have a duplicate there. And so there we dropped the amount of duplicates from 126 down to 1. One thing I want to try is I'm looking for my my duplicate data generator. Okay, it's not running, but anyway, so here you see a technique for using, and if I come down here again, you're going to see the schema and the fact that it has a replacing merge tree. So that's a key table for using when you want to deduplicate data. So now let's switch gears again. I want to show some stuff related to using the aggregating materialized view. And I have a tag around that. So what we have here is, again, we have our source stream, eSource stream. That's the one we first started with. And I'm going to build a new pipe. And we're going to call this feed hourly revenue MV. And we're going to build a node here. Here's where we're going to be doing some aggregates. So let's see if I can type this fast enough. We're going to do, this is a ClickHouse function that represents or is an example of all the different types of time series functions that they provide that Tinybird implements. here I'm basically binning data to the start of an hour. And if you ever written SQL without these type of functions, you probably know that binning data, the queries can get quite involved. But with this dialect of SQL, it's quite easy. So here I'm going to do things like, I want the count of how many sales we've had. And remember the state variable, because I'm telling the system, hey, as stuff comes in, maintain these pieces and apply this transformation as it rolls. I'm also going to do a sum state. Here I'm also looking at price, and I want to do that as the revenue for that hour. And I'm taking from, not that, I'm taking from our purchases. Because remember, I've already segregated all the purchase data with the price information into this new materialized view. And I guess this is another example of chaining these things together. So I also want to do a group by. I can type. And I want to do by timestamp. And well, there we go. And let's run this. All right, so you'll see here that because I've used the state, you're not going to see these values. It's just, this is a visual that, hey, you've triggered this aggregated state. And now it's up to us to go out and build a pipe that will merge those temporary things into the final answer. So I want to create another materialized view here. I want to select the one node I have. I'm going to call this hourly revenue MV. I want to go to advanced. You can see here that because I used the state form of those aggregation functions, it already knew that I would be going to an aggregating merge tree. So let's do the same thing. I'm going to pull in and create all these values. And I'm going to, let's go look at this hourly revenue. And you can see here too, it's aggregated state. So now I have to build a pipe that's going to pull from that. And I already have one set up. And if I run this, you'll see that I'm using the merge, the count merge in this case for the count itself. And then for the sum, I'm using the sum merge. So again, what this is telling the system is that, hey, you have this corpus of data you've already pre-processed, but you also have these new blocks of data. And this is the point where I want you to do the work to merge it. So the point being that it's only working with a very small percent of all the data that has just arrived, and it does the work of merging it together. And that is our demo of using aggregating merge trees. Now I see we only have about 5 minutes left. So curious if there's any questions out there. I'm going to go back to the deck and.
Can I add something about aggregating merge trees? And actually, yeah, if you go right back to that use case, I think it's something also to additionally see how powerful it is. So, while you did something here that's super powerful, right? Which is, maintaining this, reducing the amount of rows scanned because you were maintaining state and aggregating per hour. But the interesting thing is that we don't necessarily have to aggregate by just one thing. We're often saying, hey, I want to aggregate, and these are just hourly revenue, right? Let's assume for a second you decided to put onto this table not only the hours, but also the store. So the beauty of aggregating merge trees is that you could actually say, let me get all the sales and revenue across all the stores, but then you can also do it per hour per store. All do it with the same MV, with the same data. And that becomes extremely powerful for you. And let's say actually you might not want to do this because of the way the sorting key is set up. You might say, I don't care about the hour. All time, what is the revenue per store? You can technically use the same MV for that and do it per store. So, the key thing is you end up having a lot of power and flexibility on how you want to aggregate. Obviously, it really depends on how you set up your sorting key, but you're not limited to have one field you're grouping by. You can have multiple fields you're grouping by. You can have one of those fields. You can have any one of those fields, ideally, as long as they're part of the sorting key and that, small low cardinality. So you get a lot of power for aggregating in whichever way you want to see the data. So it really helps with a lot of the slicing dicing capabilities. And it's something we don't see very often when we're talking about MVs, but it is one of the superpowers of a materialized view. And because of that fact that it holds the aggregate state under the hood, regardless of how you aggregate and decide to aggregate, it'll know how to take that state and roll it up for you. Imagine trying to do this in a traditional DMS, DBMS with traditional MVs. This would be this would be an absolute ridiculously difficult problem to solve for, and maintaining different kinds of aggregation states.
Right. And Ariel, can you share any stories? Were you in your previous life before you joined Tinybird? Were you in a situation where materialized views and how you may have been doing them before affected how you landed at Tinybird in terms of using it as a product? Or
well, I mean, not how we were using them before, but definitely for solving a very difficult problem, which is, in my previous world, what we were doing is we had to do a lot of pre-aggregation in Spark. So we were doing this using an approach on Databricks on Spark. We were streaming data and we were calculating averages in a streaming fashion and then writing those down to other places. Doing it with Tinybird made it really, really simple and easy because of the average states. So we were able to maintain all this data, all these calculations in SQL, where we didn't have to run streaming data calculations in Spark and another bit of code. We could actually remove all that code and just do it in Tinybird. The other thing that I found that was very powerful in Tinybird was this exact ability that I talked about before, which is I can aggregate by this, or by this and this, or by this and this and this, all with the same MV, which in any other approach, even including what we did, streaming in memory with Spark, would have been a lot more resource intensive and a lot more complex.
Yeah, right. Okay. I wanted to go back to my deduplicating example. I just restarted my process with duplicate data. And I can see here, I just wanted to show this one more time. When I look back at the last 10 minutes since I restarted, I have 12 duplicates in my duplicates table. That's expected. But then here you see that after I've sent it through a replacing merge tree, I just wanted to play again with this final. Because if I run this query without final, I think if the timing's right, I'm probably going to end up with 1 or 2 duplicates that have not been, eliminated by the normal merge process under the hood. Unfortunately, I don't see any evidence of that. So anyway, but when you're using these replace and merge trees, you do always want to use the final keyword that tells the system like, hey, regardless of how quickly you've been merging things, do it again now. And even if there were temporary duplicates in that table, by using the final word, you can eliminate them. So I wanted to get back to what next steps. We're up against time. Again, we do have this Materialized View workshop repository. A lot of the material I presented is in here, but maybe also importantly in the Tinybird folder, we have data sources and pipes that we demonstrated today, along with some narrative about how we set these things up. And also you can, I would encourage you to play with building your own materialized views. Here's a quick URL. You can go to just sign up if you have never signed up for Tinybird before. And of course, we have a community Slack channel. It's an impressive array of folks active in that community, both my fellow Tinybird colleagues, but also a great set of power users and people who are brand new to the platform, generally just helping each other with questions and understanding how to build. So thanks again, everybody, for coming today. Look at our, I'll show you. We have a live page. This is where you can keep track of sessions that are scheduled for the future. And actually, we're going through and debating what to present on next. If you have any burning questions or topics you'd like to be covered, certainly let us know. But also, you can come here to this page to see what we've presented over the last many months. So again, thanks everybody for coming, and hope you've learned enough about materialized views to start implementing them in your own system. Goodbye, everyone.